Good morning and welcome to today's Energy Subcommittee hearing on the Department of Energy's DOE Energy Innovation Hubs. This hearing will establish congressional oversight over the 4 existing hubs, examining the costs and benefits of the department's approach to collaborative research and development. DOE Energy Innovation Hubs are designed to coordinate research efforts across the department, encouraging cooperation between researchers in basic science, applied energy, and engineering, and bringing together researchers from the national labs, academia, and industry into teams which are focused on solving critical energy challenges. With appropriate goals, benchmarks, and oversight, this kind of collaborative research and development is just plain old common sense. Through the national labs, the federal government has the expertise to conduct basic and applied research, while the private sector has the ability and the motivation to move the next generation energy technology into the marketplace. The department funds the 4 energy innovation hubs at approximately $90 million per year. The existing hubs are focused on a number of energy challenges, including extending the life of nuclear power reactors, developing better and more powerful batteries, creating new materials for advanced energy technology, and mimicking the ability that plants have to create fuels from sunlight. The Consortium for Advanced Simulation of Light Water Reactors, also known as CASL or CASL, brings together our best and brightest from industry, the academia, and the labs to develop codes to model and simulate operations of the U.S. reactor fleet. These cutting-edge tools allow us to increase our return on our investment from DOE's supercomputers within the Office of Science's Advanced Scientific Computing Research Program, the subject of a hearing we held in this Energy Subcommittee earlier this year. One critical application of CASL's virtual environment for reactor applications, known as VERA for short, is to enable the nuclear industry and regulators to predict the performance of reactor components for license renewals by the Nuclear Regulatory Commission, NRC. I'd like everyone to take note of the slide on the screen. Have we got that up, Aaron? Which shows what is at stake. It's called The Clock is Ticking. Which shows what is at stake for the nation's base load electricity from nuclear power if the operating fleet is unable to secure license renewals to 60 years and 80 years of operating life, respectively. And it shows it there on either one of our slides. These NRC license renewals are an important issue for the reliability of our nation's electricity and for my district on the Texas Gulf Coast. The South Texas project, currently operating near my district, which I used to represent, by the way, as you gentlemen know, provides reliable zero-emission electricity to the state of Texas and good-paying jobs for my constituents. It's pretty clear from this graph just how important these licenses are to maintaining reliable, affordable power across the country. I know that Dr. Jean has provided a similar figure in his prepared testimony, so I look forward to discussing this important issue today. The research and development underway in the CASL Hub is just one example of the benefits from this collaborative research approach. The technical expertise and scientific facilities in our national labs can provide tremendous impact on the private sector through appropriate partnerships. However, while the current DOE Hubs program pursues worthy research goals, not all collaborative research is a guaranteed success. In the first round of hubs in the program, DOE established a hub focused on building efficiency. But due to cost, poor performance, and lack of clear goals, this hub was dissolved. Establishing a new hub, center, or project is not the answer to every problem, and new proposals must be appropriately justified to Congress and shown to meet the research and development goals for the lead DOE office. Any authorization of new or continuing hubs proposed by DOE must also include the ability to efficiently close down projects that are not achieving clear measures of success. I want to thank our witnesses today for testifying on their valuable research and the DOE Energy Innovation Hub program. I look forward to a discussion about federal government's role in leading collaborative research and development and how to leverage limited taxpayer dollars for the greatest economic impact and scientific achievement. So, I'm going to recognize the ranking member, Mr. Grayson, for an opening statement. He's chomping at the bit.
Thank you, Chairman Weber, for holding this hearing, and thank you to our witnesses for joining us today. I'm pleased to see that we have the director of each Energy Innovation Hub here this morning. These hubs seek to accelerate scientific discoveries that address critical energy issues, particularly barriers to advancing new energy technology. Today's hearing is well timed. 2 of the 4 existing innovation hubs are up for renewal this year, while the others are just beginning. The Energy Innovation Hub program was established only 5 years ago, and this hearing will provide to members an important opportunity to understand further what must be done to ensure the success of existing and future hubs. Unfortunately, Congress has yet to provide any authorizing legislation for the important work being performed at each of the hubs. I hope that today's hearing will provide the foundation needed to accomplish that goal. Toward that end, I have already introduced H.R. 1870, a bill that would establish merit-based rules governing the selection, scope, and composition of future hubs. Further, the committee has accepted the legislative language from that bill as an amendment to the America Competes Reauthorization Act, which was considered on the House floor less than a month ago. I appreciate the chairman and his staff's efforts to work together to ensure that this important provision was included in the final bill. I also want to thank Ranking Member Johnson for including it in the alternative competes legislation produced by the minority that was offered as a substitute amendment both in committee and on the floor. I'm very excited about the possibility of our committee finally producing authorizing legislation for energy innovation hubs. There are some issues I look forward to learning about this morning, particularly issues regarding hub management and length of operation. We need to develop a plan for hubs that reach the end of their second 5-year contract. Presently, the department is indicating that hubs will continue to work for a maximum of 10 years only. I support this guidance in principle because it fosters a sense of urgency within hubs to define and achieve goals as expeditiously as possible. But what happens when a hub has been extraordinarily successful? Maybe there should be some process through which, according to merit-based review, that hub is permitted to continue pursuing promising research and maybe even profound new discoveries. The answers to these questions and others are what I'm looking forward to hearing from you all today. I also look forward to hearing each of your views as to how your own hub works in the context of Department of Energy research activities and goals across the board. How specifically is the research that you're performing contributing to the larger effort to solve our nation's pressing energy challenges and needs? Each of you is involved in exciting and innovative work. I look forward to hearing from you and watching each of your hubs as they progress. It's my hope that Congress can provide to you the resources that you need to accomplish your goals, and I look forward to working with you, Chairman Weber, toward that end. Thank you. I yield the balance of my time.
I thank the gentleman. Let me introduce our witnesses.
Thank you.
Our first witness today is Dr. Harry Atwater, Director of the Joint Center for Artificial Photosynthesis, or JCAP. In addition to his position at JCAP, Dr. Atwater serves as the Howard Hughes Professor of Applied Physics and Materials Science at the California Institute of Technology. He specializes in photovoltaics and solar energy, as well as plasmonics and optical materials. Dr. Atwater received his bachelor's degree, master's degree, and PhD in electrical engineering from the Massachusetts Institute of Technology. Our next witness, and welcome, by the way, Dr. Atwater. Our next witness is Dr. Jess Jean, Director of the Consortium for Advanced Simulation of Light Water Reactors, or CASL. Dr. Jean has been with the Oak Ridge National Laboratory for over 20 years. Prior to his current position, Dr. Jean was a senior R&D staff member performing research primarily in the area of nuclear reactor physics. Dr. Jean received his bachelor's degree in nuclear engineering from Kansas State University, his master's degree and PhD in nuclear engineering from MIT. And by the way, welcome, Dr. Jean. And I will now yield to the gentleman from Illinois, Mr. Lipinski, to introduce our next witness.
Thank you, Chairman Weber, and thank you, Chairman and the Ranking Member Grayson, for holding this hearing. It's my honor to introduce Dr. George Crabtree, who is the Director of Joint Center for Energy Storage Research, or JCESR, at Argonne National Lab, which is in my district. He is also a Distinguished Professor of Physics, Electrical, and Mechanical Engineering at the University of Illinois at Chicago, serving as a bridge between Argonne and academia. He has won numerous awards for his research, including the Kamoling-Onoz Prize for his work on vortices and high-temperature superconductors. This prestigious prize is awarded once every 3 years. Dr. Crabtree is the second recipient. He has won the U.S. Department of Energy's Award for Outstanding Scientific Accomplishment in solid-state physics 4 times, which is a very notable accomplishment. Dr. Crabtree has served as Director of the Materials Science Division at Argonne. He has published more than 400 papers in leading scientific journals, has collected over 16,000 career citations, and has given over 100 invited talks at national and international scientific conferences. His research interests include next-generation battery materials, sustainable energy, energy policy, materials science, nanoscale superconductors and magnets, and highly correlated electrons and metals. Dr. Crabtree co-chaired the Undersecretary of Energy's assessment of DOE's applied energy programs. I want to thank Dr. Crabtree for joining us today, and look forward to your testimony.
Thank you, gentlemen. Welcome, Dr. Crabtree. Did he say 16,000 citations? I don't know how you can afford that. Every time I get a citation, my insurance goes up. Yours has got to be astronomical. Our final witness is Dr. Alex King, Director of the Critical Minerals Institute, CMI. Before joining CMI, Dr. King served as the Director of the Ames Laboratory. Dr. King received his bachelor's degree in physical metallurgy from the University of Sheffield and his PhD in metallurgy and science of materials from the University of Oxford. Welcome, Dr. King. At this time, I'm going to now recognize Dr. Atwater for 5 minutes to present his testimony. Dr. Atwater.
Okay, thank you, Mr. Chairman, distinguished members, ladies and gentlemen. It's my pleasure to be here today to tell you about the work, the mission, and the progress of the Joint Center for Artificial Photosynthesis. And so I think it's fair to say that having a source of renewable fuels would be a great source of energy security, economic well-being, and environmental protection for the United States. And JCAP, which is a partnership that's led by Caltech, but also with major partnerships with the national labs, Lawrence Berkeley National Labs and Stanford Linear Accelerator Lab, as well as the University of California, is focusing on building the scientific foundation for renewable synthesis of transportation fuels directly from sunlight, water, and carbon dioxide using a process called artificial photosynthesis, or otherwise known as generating fuels from sunlight. So most people are familiar with the idea of generating electricity from sunlight with solar panels that you might put on your roof. So what JCAP is working on is the science behind taking those charge carriers and directly converting those charge carriers that come out of your solar panel into chemical fuels, examples of which are hydrogen, which we generate by splitting water into hydrogen and oxygen, and generating renewable carbon-based fuels by reduction of carbon dioxide. And JCAP was established in 2010, and during its first 5 years had a primary emphasis on hydrogen production, and in its missionary objective, sort of overarching missionary objective during that time, was to develop a robust solar fuel generator for hydrogen generation that operates 10 times more efficiently than natural systems like plants and crops. And I'm happy to say that JCAP has been able to meet that objective of developing a robust solar fuels generator, and more importantly, really developing the concept of what a solar fuels generator is. That's been an important contribution to the scientific field and to the advancement of technology. In its next 5 years in renewal, JCAP is going to focus on, as a main objective, reduction of CO2 and converting reduction of CO2 to transportation fuels, direct transportation fuels. And this is really also, in addition to a strategic objective for making fuels, it is really a dramatic scientific grand challenge, the reduction of CO2 selectively producing exactly one product and not a bunch of byproducts is a true scientific grand challenge. So to date, we have, as I indicated, been able to develop solar fuels generators that operate 10 times more efficiently than plants. And that has really set the stage for a follow-on generation of applied R&D that can develop the scalable generators. And as you may know, there is no existing solar fuels industry. While there's a solar panel industry, there is no solar fuels industry. So it's these innovations that will really set the stage for a U.S. industry, a new U.S. industry in this area. And in the course of its work in generating solar fuels generators, JCAP also discovered new catalysts for water oxidation and reduction. Importantly, a method to protect semiconductors against corrosion so they can be long-lasting and robust in their operation. And in addition to these scientific discoveries, JCAP established a number of important facilities, including 2 state-of-the-art labs, one at the California Institute of Technology and one at Lawrence Berkeley Laboratories, that are purpose-built for solar fuels research. It established new methods for rapid, high-throughput screening of materials, so we can do experiments that used to take years in matters of weeks. We developed the first facility for so-called benchmarking, or developing standard test conditions for evaluating catalysts so that we can understand how different solar fuels materials operate and perform. We developed new methods for characterization of solar fuels materials using advanced X-ray light source techniques at the Advanced Light Source at Lawrence Berkeley Labs and Stanford Linear Accelerator Lab. Also, to set the stage for a new solar fuels industry, JCAP has been very active in developing invention disclosures, a total of 36 invention disclosures and 26 patent applications, which are available for licensing to industry. And has a output of scientific results, 200 papers, 60% of which are in high-impact journals, and numerous keynote and invited presentations by research scientists in JCAP. So just to highlight some of the things that, why is it that a hub is an appropriate mechanism to carry on and accelerate this kind of research? JCAP has been able to leverage the integrative hub concept to make significant advances, one of which I cited earlier, which is the notion that we could accelerate the development of catalyst materials in a timescale that normally takes years in this sort of conventional pace of progress in science, and carry out that in a matter of weeks. And so as an example, in 2013, JCAP developed, by a collaboration between 2 of the JCAP projects, the High Throughput Experiment Project and the Heterogeneous Catalysis Project, new catalyst materials composed of 4 elements. And there are many, many ways you can combine 4 elements together in different compositions. And so a very large number of samples were made and rapidly screened using high throughput combinatorial synthesis techniques that allowed us to very rapidly identify candidates. And promising candidates were scaled up and tested at the laboratory level, really accelerating that pace of progress. Another example is the development of a cross-cutting, what we call process materials and integration team, a group of applied and basic research scientists that came together from across JCAP to really understand how to put together and design and build very rapidly solar fuels generator prototypes, so we could understand what works and what doesn't on a rapid time scale. So those are many of the key accomplishments. And so for the future, JCAP is going to focus on the grand challenge of scientific grand challenge of reduction of carbon dioxide and generation of liquid fuels directly from the products, reduced products. This is an area that takes JCAP, which has a translational mission, sort of more upstream in the basic research end, because in the area of carbon dioxide reduction, there are many more scientific challenges and unanswered questions than I think it currently exists for the case of hydrogen production. And so it's the opportunity to really unlock the mechanisms and the scientific discoveries that could selectively reduce CO2 to fuel products that could generate a new generation of generators for liquid fuels. And that's going to be our missionary objective as a scientific grand challenge and setting the stage for a new type of solar fuel generator.
Thank you, Dr. Atwater. Dr. Jean?
Thank you very much, Chairman Weber, Ranking Member Grayson, and members of the subcommittee. It's my honor to be here to provide this testimony on the Energy Innovation Hub Integrated Research Approach. CASTLE was the first hub established by the Department of Energy in July 2010. It's currently completing its first 5-year term. It consists of 10 core founding partner institutions from academia, national laboratories, and industries led by Oak Ridge National Laboratory. Our focus is on innovations in nuclear commercial power generation, specifically the advanced modeling and simulation of nuclear reactors. CASTLE's vision is to predict with confidence the performance of nuclear reactors through comprehensive science-based modeling and simulation technology that is deployed and applied broadly throughout the nuclear energy industry to enhance safety, reliability, and economics. CASTLE is capitalizing on advancements in computing and is helping retain and strengthen U.S. leadership in two key DOE mission areas of high-performance computing and nuclear energy. CASTLE targets R&D and technical areas that have been selected as significant current industry challenges where modeling simulation can provide meaningful advancements, particularly to help achieve increases in operating power, life extensions, and higher fuel utilization. Many of the CASTLE developments are focused on key phenomena that limit power generation, and so they can improve operations. Similarly, a significant benefit can be achieved through further life extensions by ensuring that reactor life-limiting components can meet their design requirements for longer operating periods beyond the current license renewals. CASTLE's integrated research model is based on establishing an organization with outstanding researchers with a clear and agile research plan. Let me point out a few of the key features of this integrated model. Central integrated management, decision-making, and program integration, strong science, engineering, applications, and design leadership, independent oversight and review by an external board of directors, science and industry councils for oversight, review, and advice, an agile work process based on 6-month planning execution periods. In order to achieve our research goals, CASTLE is developing a virtual reactor that we call VERA, which stands for the Virtual Environment for Reactor Applications. Our key research accomplishments in development of VERA include creating a comprehensive hub environment that supports a large team of researchers working on developing, testing, and employing VERA, the virtual reactor, developing the computational methods and computer codes for all key physics needed to model reactor operation, applying VERA to simulate several nuclear power plants, including the Watts Bar nuclear plant near Oak Ridge, which was designed by Westinghouse and operated by TVA, both partners in CASTLE, and coupling of physics software components and models with initial applications providing integrated simulation capabilities not previously available. A key metric of the success of CASTLE's modeling and simulation capabilities is deployment to nuclear industry, where these tools can be used. In order to achieve this, we have strong engagement with our industry partners and a broad connection with private industry through the integration of more than 50 additional contributing partners. CASTLE also relies on an industry-led industry council with over 25 members from the broader nuclear energy and modeling simulation industries. VERA has already been deployed to industry engineering environments through CASTLE test stands. This includes, for example, the use of Vera at Westinghouse for simulating the AP1000 reactor to confirm their own engineering calculations. In Castle's second 5-year term, Vera will be expanded beyond pressurized water reactors to support boiling water reactors, which represent the remainder of our current operating fleet. We will also consider future light water reactor designs, including small modular reactors. In conclusion, energy innovation hubs represent an effective research model that enables Castle to conduct basic and applied research for critical energy application. Through the hub model, Castle has tapped into DOE advanced computing strengths and nuclear energy research capabilities. We've taken advantage of the best and brightest university researchers, and we've integrated decades of industry experience and expertise. This highly integrated, focused R&D partnership has demonstrated accomplishments at a rapid pace, notably including successful deployments to several industry end users. As the first energy innovation hub, Castle has clearly demonstrated that this research model can be a very effective method to deliver targeted research and rapid solutions to address complex issues. Thank you very much.
Thank you, Doctor. Dr. Crabtree.
Thank you, Chairman Weber and Ranking Member Grayson and members of the committee for this opportunity to testify. I will be talking about the Joint Center for Energy Storage Research, otherwise known as JCESR, which addresses two compelling challenges: creating the next generation of high-performance, inexpensive electricity storage to transform transportation through the widespread penetration of electric cars, and to transform the electricity grid through widespread penetration of clean and sustainable wind and solar energy. JCESR concentrates exclusively on next-generation electricity storage beyond the reach of today's lithium-ion technology. Transportation and the grid account for 2/3 of all the energy used in the United States. Transforming them with high-performance, inexpensive storage not only modernizes our energy system, but also grows the economy, creates jobs, and promotes U.S. innovation in the global marketplace. JCESR brings a new paradigm to battery R&D, integrating 4 functions into a single, highly interactive organization. And those 4 functions are discovery science, battery design, research prototyping, and manufacturing collaboration. It is close interaction spanning across these 4 functions that accelerates the pace of discovery and innovation and shortens the time from conceptualization to commercialization. So JCESR's new paradigm is a model not only for battery R&D, but also for other critical national energy challenges. Using our new paradigm, JCESR intends to create 2 additional outcomes or legacies: a library of fundamental science of energy storage, applying the remarkable advances of nanoscience of the last 15 years to the materials and phenomena of energy storage at atomic and molecular levels. And the second outcome, using this new understanding to deliver 2 prototype batteries, one for transportation, one for the grid, that when scaled to manufacturing have 5 times the energy density and 1/5 the cost of today's commercial lithium-ion batteries. Although the 2 batteries may look very different, they will be based on the same library of fundamental science. JCESR has already made substantial progress toward its goals. Soon after launch, we established our new paradigm, spanning 150 researchers at 14 partner institutions. We began building the personal relationships that enable intense and effective communication, and we put in place the strategic objectives and the daily meetings that drive our program. In its first year, JCESR established 3 distinguishing tools. So materials genome approaches for crystalline electrodes and liquid electrolytes that simulate tens of thousands of materials on the computer to find the most promising ones before they're ever made in the laboratory. We also put together a unique electrochemical discovery lab to synthesize and explore these materials with state-of-the-art tools. And the third distinguishing tool is techno-economic modeling to simulate the performance and cost of complete battery systems on the computer before they're prototyped. So JCESR used these tools to make foundational progress in all 4 of its functional areas. We identified 4 promising directions for transportation and grid prototypes. We used our tools to converge these 4 battery prototypes So techno-economic modeling revealed the ultimate performance of each of the 4 prototypes, and in an inverse process provided performance and cost thresholds for the materials that would make up the components of those batteries. The materials genomes found promising materials to meet these thresholds, and the synthesis and prototyping teams began to build partial and complete prototypes to test the compatibility of the materials as complete battery systems. So we've met extensively with the private sector to discuss the size and performance of J. Caesar's prototypes that would be required to translate them to commercialization. In our 2.5 years of operation, we've learned the critical importance of continuous improvement of our new paradigm. We work closely with our 14 partners, our 150 researchers, and our sponsor, the Office of Basic Energy Sciences and DOE, to refine our management practices, to refine our strategic directions, and to balance our exploratory divergent research to identify promising solutions with focused convergent research to implement and complete the selected solutions and prototypes rapidly. During this time, we've terminated research on one candidate prototype, that would be lithium-oxygen batteries, and initiated research on other promising opportunities, including metal anodes for lithium and magnesium, and membranes for flow batteries. Nimble response to management and strategic challenges and opportunities as they arise is essential for completing our mission in a timely manner. So thank you again for the opportunity to testify, and happy to answer questions later on.
Thank you, Dr. Crabtree. Dr. King.
Thank you, Chairman Weber, Ranking Member Grayson, members of the subcommittee. Thank you for the opportunity to testify on today's hearing on the innovation hubs. I'm director of the Critical Materials Institute, which is led by the Ames Lab in Ames, Iowa, the U.S. Department of Energy Office of Science National Lab operated by Iowa State University. CMI's team includes more than 300 researchers and support staff across 6 corporations, 7 universities, and 4 national labs. CMI exists primarily to mitigate the challenges posed to the manufacturing sector by materials that provide essential functions or capabilities but are subject to supply risks. The hub focuses on materials used in clean energy technologies, but many of these have broader uses, notably in the area of defense. Prominent among the hub's research targets are the rare earth elements, which are used in magnets, lighting, and displays, and lithium, which is used in today's rechargeable batteries. CMI follows the critical materials strategy developed by the U.S. Department of Energy, addressing opportunities in 3 areas. 1, diversification of supply. 2, development of substitute materials. And 3, improving the efficiency of materials use and reducing waste in our access of the currently available materials. Within its first 5 years, this hub will develop and have adopted by industry at least one technology in each of these 3 areas. In its first 2 years of operation, we just celebrated our 2nd anniversary, CMI has developed 34 inventions with significant potential for impact, has made 4 patent applications. It is very close to having 1 replacement material adopted by an industrial partner and is within a year or 2 of a second. Materials development of this kind typically takes 20 years, and we've succeeded in 2. Maybe I'll explain how later. The CMI-developed technology for solvent extraction is being considered for licensing by 2 mining companies as we speak. These results have strong potential for providing financial returns on the investments made by the U.S. taxpayer. The hub has earned an international reputation and has been described as the gold standard in its field. Several other countries are modeling their own efforts after CMI. How does this integrated research model advance the goals of the Office of Science and applied programs at DOE? Let me offer an example. In pursuit of new magnet models, we combine, as other hubs do, computer simulations, experimental exploration of candidate alloys, rapid analysis and testing. These methods are all founded upon tools previously developed among CMI's partners, largely with DOE Office of Science support, but we have advanced them and made them specific to our own purposes. So the hub has, in its first 2 years, developed the first successful theory and computer model for predicting what is called magnetocrystalline anisotropy. Maybe I'll explain if you ask, for proposed new materials. This is something that hadn't been possible before. It's a contribution from fundamental condensed matter physics in support of developing new magnetic materials. We've developed a tool based on additive manufacturing technologies for the rapid production of target magnet compositions, allowing us to produce arrays of materials that can then be tested. We've built new capabilities, actually in collaboration with JCAP, for rapid analysis of materials that take advantage of our additive manufacturing tool. And we have added high-throughput magnet testing capabilities. All of these capabilities work together to produce new materials, make them, test them, and meet the needs of the hub. They are also enhancing the capabilities of other Office of Science and EERE programs. Bringing them together, we have created a range of candidate materials for new high-performance magnets. Effectively, what we have done is to orchestrate diverse scientific efforts and enhance them so that we're able to meet technological needs of the day in short order. We've demonstrated the ability by doing that to go from 0 to having new materials invented in 2 years, a process that typically takes up to 20. How does the private sector interact with CMI? We are very flexible. We have always sought to be flexible and responsive to industry needs. We find that our research goes faster when we speak to industry because when speaking, first we listen. We foster increasingly intense collaborations as companies move from informal interactions to membership in our affiliates program to full engagement as research team members. Some companies have also expressed interest in engaging CMI for proprietary pre-commercial research, and we are considering that opportunity. Technologies developed by the Hub using its federal funds must be pre-competitive, must have high potential for impact on the supply chain, must be cost-effective, timely, and have potential for adoption by U.S.-based companies. Thank you.
Thank you, Dr. King. I thank the witnesses for your testimony. I now recognize myself for questions for 5 minutes. Dr. Jean, as I noted in my opening statement, CASTL's support for NRC license renewals is an issue of particular importance to my district, mine adjoining Matagorda County, or Blake Farenthol's district. The South Texas Project Units 1 and 2 are currently under review by the NRC to operate for an additional 20 years, which means 20 more years of safe, reliable, and I might add, zero-emission power for Texans. Can you explain to us generally how CASTLE simulation capabilities uniquely allow the use of supercomputers to model the integrity of a reactor pressure vessel and other components, and why this is important for license extensions for the reactor fleet to operate up to 80 years? Doctor?
Yeah, thank you very much for the question. So in a life extension of a reactor, you need to consider the aging of the materials. And so this is being done for the current 20-year life extensions. What we're interested in is informing the next 20-year extension, which you have noted 60 to 80 years. So it will not impact the current, CASTLE will not impact the current license renewal, which is already in process. When you look at the extension to 60 to 80 years, there are critical components in the reactor that can't easily be replaced. One of these is the reactor vessel. There's others that are concrete and other materials.
Let me ask you real quick, right in here, because I read that in your comments.
Yes.
Why is it that the reactor core cannot be replaced? Is it just cost prohibitive?
It's cost prohibitive. Would be very evasive. to extract the vessel or the reactor vessel, which is right in the center of the reactor. So it's not deemed as being cost effective to replace.
Okay, that's strictly based on cost considerations.
Yes.
Okay, thank you. Go ahead.
And so, but the integrity of that vessel is really very important, of course, for safety and operation reasons. So it's important to look at its integrity, and which is done extensively in renewals. What we're doing in Castle by using our supercomputing capabilities is be able to do a very precise calculation of the neutron interactions on that vessel. So the vessel surrounds the fuel, and so neutrons move around in the core, hit the vessel, and affect its material properties. So by being able to better follow the operation of the reactor over its lifetime and calculate the neutron interactions in a better way, three-dimensional, higher fidelity, you can combine that with improved material models that are being developed to understand the condition of that vessel and ensure that it can be extended another 20 years.
We were talking earlier when I came out to introduce myself to y'all about criticality.
Yes.
Once that process is, how long does it take to reach criticality, for example?
They load the fuel, and it might take a day or two to become critical, and then there's an escalation in power over a couple days, and then the intention is to operate at full power. Critical means operating exactly steady state power. That's where you want a reactor to operate for 18 months. That's the goal, and then you shut down for refueling.
So once you reach criticality, and you've got, forgive me, this is very technical, neutrons, explain the process.
Yeah, so the goal in achieving criticality or steady state operation is to have a self-sustaining neutron chain reaction. And so you get neutrons that are produced by fission, and you have those in balance such that they cause additional fissions that create more neutrons, and you maintain a steady state.
Right, and of course I'm a layman in this, but it just seems like once you reach criticality, you know the effect on the reactor core.
Well, so when you reach criticality, you are impacting the fuel, you're depleting the fuel, you're irradiating the vessel, irradiating the components, and most importantly, generating power, which is the whole reason you're doing this. So while you're doing that, you do not know the full three-dimensional distribution of fluents on the vessel. You make measurements in selected locations to confirm the material behavior is as expected. But what we can add with Castle is a lot more detail than what can actually be measured.
Are you measuring inside and outside the vessel?
Yeah, they insert what's called coupons, or metal samples that they can then take out of the reactor and interrogate. So one thing is really important. Simulation alone can't provide this information. It's simulation combined with this type of data and experiments that can give the complete picture.
Are you able to anticipate new materials? I know that some we talked about graphite being used, heavy water, light water.
Yeah.
Are you able to extrapolate that to what those effects would be on the core, the reactor core itself?
Yes, and the tools we're developing are based on more fundamental principles than typical design tools. So they'll accommodate different consideration of different materials. It's particularly valuable in scoping calculations. What if we did this? How would it perform? So you could down select to the most promising concepts that you could then take forward. This is looking at fuel designs and how you operate the reactor can give you a lot more additional information.
Okay, forgive me, I'm way over my time, but I did have a question for Dr. Crabtree. I think you're working on the batteries. All I want to know is, can you make it where my iPhone battery doesn't run down while I'm watching the grandkids on videos? So.
Great question, and I have the same challenge.
Right.
I wish my iPhone lasted twice as long.
Thank you very much, and I'll now yield to the ranking member.
Thank you. I have some questions for Dr. Atwater. I'm going to try to understand better how the research that you're doing fits into the bigger picture of energy production and storage. What you described is an effort to create solar fuels as opposed to the more typical effort to create electricity from solar power. Is that correct?
That's right, yeah.
All right. So is that similar, would you agree, to something like ethanol production, or is that different?
Well, so ethanol is an example of a chemical fuel. That's a liquid fuel that's suitable as a liquid fuel. And that is indeed what ethanol is normally produced by, for example, fermentation of feedstocks from crops and plants and so forth. And that's a process that is established, but it's limited by the efficiency of natural photosynthesis. So what artificial photosynthesis, or fuels from sunlight, in the research objectives of JCAP, is focused on the same process of chemical fuel production, but with a much higher efficiency. So the efficiency potential for fuel production rivals that of the efficiency potential for photovoltaic systems. For example, if you put solar panels on your rooftop, you can expect that the solar panels will operate with an efficiency for electricity production of something like 20% of the total sunlight falling on your rooftop. For example, natural photosynthesis is less than 1% efficient for most plants and photosynthetic organisms. So there's a big gap there. And so JCAP is working to develop processes that can make fuels very selectively. We want to make one fuel, say ethanol or methanol or hydrogen, and not a bunch of byproducts. Nature does this, of course, very well. But nature is not particularly efficient. And so to make an economical source of fuel generation that can generate and foster a new industry, we are focused on efficiency. And like the nuclear hub, I would mention, we're focused on reliability, because if you think about the return on investment for any solar panel that you would put on your roof, it has to last for a long time. It has to last for 20 or 30 years in order to get that return on investment. Similarly, we want to make devices that are robust and reliable that last for a long time.
So are you trying to basically do what biology does through only chemical and physical means, or are you trying to take biological processes and tweak them and improve them?
Yeah. In JCAP, we have a very sharply focused research program that's focused on chemical catalytic processes and physical processes for the charge generation. So we're using, actually, for the source of energy generation, semiconductors, very much like the semiconductors that are used in solar panels to generate electricity. But the charge carriers are then driven to chemical catalysts, not biological. So we're working on non-biological routes. And as I indicated, we've already been able to achieve efficiencies for hydrogen production that are of the order of 10% and 10 times greater, more than 10 times greater than that for natural photosynthetic processes.
So the fuel that you've created so far is hydrogen, not a traditional transportation fuel.
That's
now
right.
You're going to try to branch out into something that you could actually put into a car.
That's right.
These days, like octane or ethanol or methanol or something.
That's right, exactly. So the grand challenge is under mild chemical conditions, very much like the way a solar panel would operate, can we generate directly a chemical fuel without having to build another large plant to do the downstream distillation and refinement?
One of the more interesting things about solar power production is that there are arguments in favor of large-scale production, arguments in favor of small-scale production. Are you finding any sort of economies of scale that would tilt you toward large-scale production for this purpose, or not?
So we have done, the best way to answer that is to look at the record of an industry, and we don't have an existing solar field industry. However, JCAP has done some studies of the scalability. So what would it look like, and what would be the key drivers for improved efficiency and cost reduction if you were to build, say, a 1 gigawatt scale plant? That's a very large scale plant. For example, a conventional power reactor would be of the order of hundreds of megawatts to a gigawatt. And what you see is that the primary drivers of the cost and the economic return are the efficiency and the durability of the solar fuel generator itself. It's not the tanking and the piping and other infrastructure. So the preliminary analysis shows that the investments that we're making in the research on the technology advancement itself are the key drivers. So to answer your question directly, it looks like there's not a big sensitivity to scale.
All right, last question. Do you have any judgment yourself about the possibility or the prospect of actually taking biological processes that exist and tweaking them, improving them to the point where they can become commercially viable?
Yeah, that's a very interesting question. The wonderful thing about nature is that it's regenerative. In our bodies and in plants and so forth, cells are regenerated. And typical photosynthetic organisms only last for, minutes to hours before they die. And then nature has the benefit of regeneration. So we've really focused in our effort on non-biological routes because we want to make things, because we know that we want to make things that last for tens of years. So JCAP really is focused on chemical and physical processes, which we think, demonstrated by the record of durability of conventional solar photovoltaic panels that have the prospect of being durable for a very long time without regeneration.
Thanks. I yield back.
Thank the gentleman. I now recognize the gentleman from California. Dana, you're up.
Thank you very much, Mr. Chairman. A couple of specific questions, and is it Jenin? And did I pronounce that? Am I correct in that?
Close, Gene.
Okay, I didn't quite get that. A little louder.
Gene.
Okay. Your focus on advanced simulation for light water reactors. Light water reactors, we have a light water reactor in Orange County, and it's shut down now. And we have found all over the world where light water reactors have made things, have been put the public around those light water reactors in danger. And so now there is a danger associated with every energy source. But don't we have other potential sources of nuclear energy that are less dangerous than what light water reactors will be? And why are we stuck on light water reactors? I mean, I must have been briefed on 3 or 4 different alternatives to light water reactors that are safe and will not leave plutonium behind and can't melt down, whether they're pebble-based or thorium or high-temperature gas-cooled reactors. Why are we still putting money into light water reactors rather than going to a new generation of a different concept that wouldn't be dangerous?
So that's a very good question. I think my response will be we need to look at both. I mean, we have a large current fleet generating a lot of clean, low-cost energy that the safety record is quite good on, and so Castle's goal is to improve upon that. So, and I think we're doing that as well. There are other advanced reactor concepts. DOE is doing research on these with expectations of deployment later on in this century, and so hopefully that will be a possibility. Castle, though's focus is we have the existing fleet of 99 reactors. We're going to be adding 5 more. Let's operate those the best that we can and get all the benefits that we can.
Will the gentleman yield for just a second?
I certainly will.
I'll give you some extra time. In somebody's testimony, I read where the nuclear reactors we use on subs are safe because they're designed to shut down in the event of a military incident. Was that yours, Dr. Jenin? Do you remember?
No.
Okay. What kind of reactors are those? Are they light water reactors?
Yeah, that's my understanding. Although that's technology that the Navy protects very closely. But they put a lot of effort in the design of those reactors to ensure that they're safe.
Yeah. All right. Thank you. Reclaiming your time.
Right. Well, what we're talking about is research that was done back in the 1940s and 50s, and light water reactors are old technology. This is like trying to improve the steam engine. I mean, we can spend a lot of money improving steam engines, and in fact, I believe light water reactors are based on steam engines. Mr. Chairman, I would suggest that we are focusing our limited research dollars on light water reactors is a terrible waste and misuse of limited dollars that we have here. At the very least, we should be focusing on, if we're going to use nuclear energy, let's focus on those very promising technologies that we have not invested in yet, rather than trying to perfect something that we've been basically researching for 40 and 50 years. I'm dismayed about this, and I've been talking to the Department of Energy about this for a number of years, and we just can't get them to invest in, as I say, there's at least 3 or 4 alternatives that I know about, and I'm not a scientist. But so with this, let me ask about batteries, Mr. Crabtree. Again, are we researching old methods of batteries, or do we have some new methods? I understand that I think it's Dr. Goodenough has got some sodium based. I'm not an expert on any of this stuff. Pardon me. I'm not. You guys know much more about it than I do. But what about Dr. Goodenough's research into sodium batteries, and what's your reaction on that?
So that's a great question. J. Caesar looks exclusively beyond lithium-ion. Lithium-ion is the technology we have now that powers cell phones, although not long enough. They go out at 4 o'clock in the afternoon when you want to make a call.
Right.
And we're looking beyond that. We'd like to get a factor of 5 in performance and higher, and a factor of 5 lower in cost. So this is definitely next generation. None of the batteries that we're looking at are related to lithium-ion in their concepts or in their performance. So many people don't realize this, that the beyond lithium-ion space is very much bigger and richer than the lithium-ion space. So lithium-ion is one battery technology, been around for 25 years nearly. We know it pretty well. It can get incrementally better, but just as you were saying, we're looking for a transformative change, not an incremental change.
So let me just point out that was the right answer for nuclear energy. Okay. So thank you very much. I'm glad that you're doing what we expected our hubs to be doing. Thank you, Mr. Chairman.
The preceding comment was an editorial statement, not necessarily reflecting the view of the management. The chair now recognizes Mr. Lipinski. You're up.
Thank you, Mr. Chairman. I'm not sure I should even add anything more. I was going to ask Dr. Crabtree some questions, but what more than a endorsement from Dana Rohrabacher could there be? But I'll go ahead anyway. Battery technology, in so many ways, we know is critical for a real clean, affordable energy future. And certainly, as Mr. Rohrabacher said, it is what's being done at J. Caesar is certainly what we need to be reaching for. I mean, right now we have Tesla, Google, and Apple making investments in energy storage. Tesla announced its Gigafactory. It's going to be completed next year, but we really need to find that breakthrough technology. And I think you did a good job. My first question is going to be, how the hub works. It helps towards making a breakthrough, but I think you did a very good job of explaining how the hubs give you your hub gives you the opportunity to be very nimble in what you're doing. So that was a great example of why one of the advantages of a hub. I want to ask about the connection to industry, because I know J. Caesar has partnered with companies like Dow, Johnson Controls, and Applied Materials. Can you explain how these partnerships help J. Caesar to span the whole innovation ecosystem and help, look to the future to bring these technologies to the market?
Yeah, great question. And indeed, this was one of the things that when we made our proposal and launched our project that we had in mind. What do you do after you make the technology? How do you get it out to the marketplace? So JCI, otherwise known as Johnson Controls, happens to be right across the state line in Wisconsin from Argonne. So we go up there quite often. We spent 3 full days talking with them about what a prototype would look like that would interest them in manufacturing it. So this is something that certainly on the basic science side almost never happens. We think about the new ideas in the basic sciences, but we don't think about how to bring them to market. On the applied side, it does happen. I think JCSR is unique in that it combines both the basic science discoveries and the guidance from industry, for example, JCI, what would it take to actually be manufactured? So they can advise us, for example, don't use any materials in a certain class, they're too corrosive. We will know that from the very beginning, and at the discovery science stage, we won't be pursuing those kinds of materials. So their guidance is actually very, very important. We have another group that works with us, our affiliates, which now number 80 plus. They're startup firms, they're big companies, they're research organizations, and we talk with them all the time about their interests. So the ones that are startups, we talk about what kind of battery would you like to have. And I think it's this connection to the marketplace, which is one of the unique things about JCSR that was missing before. So Toyota will look to its own research and development organizations with its own marketing needs in mind, but they won't go outside their own house. We make it possible to go outside individual organizations.
So have you seen have you seen companies make these connections, set up locally to have the access? Does that make a difference?
Oh, it does. So there are several battery firms, usually small companies, that we work with extensively already. This does two things. It makes us familiar with what their needs are, so we can address them better, and it makes them familiar with what we can do, so they can address a question or a challenge to us that, in fact, we can respond to. So it's spilled out. You know, Argonne has a very extensive traditional battery program, lithium-ion and other things, that's not part of JCSR, but we interact with that group as well. And when we, through our affiliates and other industrial connections, we actually direct them to the right place. If it's within JCSR, that's great. If it's not, then we're part of that interaction as well.
Thank you. I have a very quick question. My little time for Dr. Atwater. I was probably now about 7, 8 years ago now. I was at J-Bay. So are you working completely something different than they are?
Yeah, that's a good question.
Go ahead.
Yeah, thank you for your question, Mr. Lipinski. So we actually have Dr. Jay Kiesling, who's the director of J-Bay, as a member of our Board of Governors, and so there's close coupling and communication between J-Bay and JCAP. J-Bay takes a focus on using alternatives to the traditional biofuels feedstocks to generate a new generation of biofuels. As I was alluding to in my response to Mr. Grayson, JCAP's focus is on using physics and chemistry to achieve the same outcomes as natural photosynthesis, using artificial photosynthesis with greater, such that the generator has greater durability and greater efficiency. So that's the primary distinction between the two.
Thank you. I yield back.
Gentleman yields back. The gentleman from Georgia is recognized.
Thank you, Mr. Chairman. And Dr. Jean, I want to circle back over to the light water reactors. Maybe take a little different approach here, but in Georgia, Plant Vogel is bringing online, hopefully very soon, 2 Westinghouse AP1000 reactors. We're actually taking a CODEL trip to visit Georgia Power here in next month to view those. In light of what Mr. Rohrbacher said, can you elaborate a little bit how Castle and Vera have been useful in licensing, ensuring the safety operations of the AP1000s, and are there should the people in Georgia be concerned, or is the technology sound? Can you elaborate a little bit on these 2 new reactors coming online?
Yeah, so thank you. It's very exciting to have these 2 reactors coming online in the South. I'm from the South, so it's great to have that more power there. I also point out Southern Company is part of our industry council, so we got interactions as well with the folks working on that plant, as well as Westinghouse, the designer of that plant. The AP1000 design has been worked on by Westinghouse and evolved and very rigorously reviewed through the NRC licensing process, and so it is got a well-founded safety basis. It enhances safety of our current fleet, incorporates lessons from Fukushima. So I think these are very impressive designs, very safe reactors. So I would not hesitate living near a reactor like that. As far as Castle, as far as the timing, was not in place to impact the licensing. AP1000 received its design certification several years ago, and the construction operating license was in place several years ago. But what we are doing, working with our Westinghouse partner, applying our tools so they can actually use these to compare to and confirm their own results and help improve their tools for future operations and when those reactors start up, so they have more information. So we expect there will be usefulness of our tools going forward, but they've not played a direct role in the current licensing of those reactors.
With reactors such as the AP1000, we're bringing these on. There's the first new reactors we brought on in how many years?
Watts Bar 1 came online in 1996. Watts Bar 2, which was started, a couple decades ago, will be online next year. And so these will be the second reactor online in this century in the U.S.
Are there obstacles that are in the way of expanding nuclear power in the nation that this body can work on?
So one of the areas that we're focused on helping, and it's broader than just Castle, is the economics of nuclear power. It does provide low-cost economics, but in competitive markets with variations, it can be rather difficult. It's it has a technical aspect that we're working on to reduce operating costs, fuel costs. There are other non-technical areas as well that probably need to be addressed. This works very well in the South, where there's a regulated electricity market where you can plan long term, so that's why you're seeing these built in the South. I think continue to improve the economics, improve the benefits that we're getting from it, but also looking at some of these non-technical issues might be worthwhile.
And one last question back on something that Mr. Rohrabacher brought up is other plants that had safety concerns. Can you elaborate on what were those, why were those plants shut down, and why is Plant Vogtle different?
Yeah, as far as I know, there are some plants that have been shut down in the U.S. I wouldn't attribute necessarily that shutdown to safety concerns. There have been issues that have resulted in an economic evaluation to not address, like replace steam generators or address steam generator issues. When you do the economic analysis, you find out the business decision is not to do that. These could be addressed. They could have been brought back. But the economic decision was not to do so.
Thank you, Mr. Chairman. I yield back.
Thank you. The gentleman from Colorado is recognized.
Thanks, Mr. Chair, and I want to thank the panelists for being here today. This is fascinating, and I'm going to ask more general questions, not as specific as some of my colleagues have asked. And Dr. King, I'd like to start with you. The purpose of these hubs, in my estimation, and as policymakers, we're trying to decide, are they working, are they not working, are they doing the kinds of things that you might expect as an experienced scientist and an administrator? Do you see these hubs as beneficial to the future of this country? And it's going to be that broad, so go for it.
Short answer, yes.
Okay. Why?
Because among many things the hubs can do is they bring us an intense focus on a particular technology or scientific challenge, and they put resources in the hands of scientific leaders who are able to, as I said in my earlier remarks, orchestrate the immense talent and tools that we have around the country to actually solve problems in very much shorter order in time than has typically been the case. So in the case of CMI, we've achieved in 2 years what typically takes 20 in a few well-selected cases. I'm not saying we can always do it.
Well, but that's the nature of science, too. Yeah. I mean, if there weren't some errors to go with the trial and errors, you wouldn't be learning much. If you knew the answer before you started, then, what's the point? So
I agree completely.
I appreciate that. So, Dr. Crabtree, my question to you is, how do you determine what the question is, what the mission is?
Wow.
And how do you put the team together?
Yeah. Great questions, and that's exactly what J. Caesar faces. I was mentioning that the beyond lithium-ion space is really rich, big, and complex, and it was really a challenge to find out where are the promising directions. So we spent about a year and a half doing that. We call that divergent research because maybe it's this solution, maybe it's that one, maybe it's that one. We've now switched in the last year to convergent research where we've picked 4 directions and we're going to implement them and make them work. But I'm sure that we're going to leave things on the table. So there will be things, even when we're done, assuming we get renewed, let's be optimistic that 8 years from now, there will still be wonderful challenges to be addressed in a similar way.
How did you put your team together? How did you determine which industry partners, which academic institutions would be part of your hub?
Great question. So the first requirement is they have to be good. They have to be the best. If we can get the best, we go for the best. If we can't, we go down a notch. And we have to be diverse. So we want to be able to look at the entire beyond lithium-ion space, not just a piece of it, but all of it, so that we can make a judgment about where are the best opportunities. We do have universities, national labs, and industry, and that's critical that it be that diverse.
I mean, if I raised my hand and I said, gee, doctor, I'd like to be part of your team, how do you vet me? I mean, I'm just a lawyer, so I wouldn't add much other than I'd try to keep you out of trouble.
We have lots of lawyers on the team, too.
All right, good.
First, we would ask, is it covered by somebody that we already have? Or is there somebody better than you? Excuse me for asking that question. Because we want to go for the best, and we don't want to duplicate. Our resources are limited, so we have to spread them around just as taxpayer dollars, you always do, in the best way. So we don't want to duplicate, and we want to cover everything.
All right. So, Dr. Jean, how long should these hubs remain in operation? Or is it in perpetuity? Or is there a finite time period? What do you expect as the administrator of your hub?
So we're expecting, and we've already done this to some degree, of having capabilities that we're deploying to industry for their use in the short term. We've done that in the first 5 years. We'll continue to do that with our renewal. With that said, these technologies require sustainability. We're looking to that as far as through our industry partners and other means of maintaining something that we develop so we don't lose it as soon as the hub ends. We're looking towards industry to do that because they're the ones who will take this technology forward. Means of performing additional research is uncertain at this time. I think we'll learn things that will lead to additional questions and insights that could be carried forward. But our current approach is within the 10 years have expanded simulation capabilities that we can hand off to and have those be applied to improve our reactor operation.
Okay. And my time's up. I'll get to you, Dr. Atwater, next go-round. Okay? I'd yield back to
Would the gentleman like an additional minute?
No, go ahead, because I got to go downstairs and ask questions.
Because I was going to take it from the gentlelady from Massachusetts. And so. Gentlelady from Massachusetts recognized.
Thank you, Mr. Chairman, and thank you to all the panelists. I also have a sort of general question for all of you, but it's been a theme that's come up. Dr. Crabtree, you referred to it. We tend to talk about basic and applied research in 2 different buckets, and really silo that. And I think it has an impact in not only how we look at science and the way the hubs are working, but also in other areas in the way we fund things and prioritize. What I'm hearing from your testimony, and we had a hearing last month where Dr. Whitaker also referenced that this is sort of a false dichotomy that we have put together. And I would love to hear in your experience in the hubs how you see this, and do you see any potential dangers in really looking at these as 2 very different siloed ways of looking at science and research?
Great question. And I would hark back to maybe 25 years ago, the time of the great industrial labs such as Bell Labs and Xerox and IBM, where they were integrated, and indeed the basic science was done right along with the application development. We've lost that. And part of that is the pressure of Wall Street. The business has to look at the next 6 months, not the next 20 years. that's hard. J. Caesar is one of the few organizations, brand new one, that bridges that gap, and it looks at a very specific problem. Unlike the old industrial labs that looked at many, many problems, we're looking at next generation energy storage only. So we're able to focus, we're able to attract the best, and we're able to integrate it across that spectrum. And I believe that this paradigm, this, as we call it, our new paradigm of doing business, doing research, may be the most important outcome of J. Caesar, that it may be a model for not only the battery community, but lots of other critical challenges where you combine the basic and the applied and actually the transition to market. So I'm actually excited about that, and I feel that we're learning now how to do it. It can be done much better than we are now doing, I'm sure of that. And if we can develop this model, we'll be way ahead of the game.
And one of my concerns is that as we look at innovation as a pipeline, if we don't start using the model that you are using, where are we going to be as we pull back? And I don't know if any of the other of you have concerns or want to comment on that. Dr. Atwater?
Yeah, let me just respond to your comment, and thanks very much for your insightful question. So JCAP, I would say, has, if you think about spanning the spectrum from fundamental research to deployment and development and scale-up, is sort of furthest upstream and has activities that start on the basic research end, but do in fact span all the way through applied research, and we provide the insights that can create the deployment decisions that have yet to be made, as we operate in an environment where there is no existing industry. But I did want to say that the progress that we've made in defining just the basic question of what does a solar fuel generator look like. We have a now well-defined model, concept of what a generator is. It has a cathode and an anode, very much like a fuel cell or a battery. It has an electrolyte. It has various components that 5 years ago, before an integrated team of scientists and engineers came together from across the applied and basic research spectrum, really didn't exist. And it's that collective synthesis of ideas and then execution of potential prototypes that led to the concepts of the solar fuels generator. So while we don't address through applied research and development yet an existing industry, the acceleration of progress that we've made actually depended on the interaction with applied researchers as well.
Great. Dr. King?
Yeah, I think the old model is fading. We certainly work with a lot of researchers who have spent their career working in fundamental research and publish a paper and worry not about how it will be commercialized. We started a process where every time we take on a fundamental research topic, we have industrial potential users come in and talk with the researchers about it. At first we were desperately worried that this would not work. What we have found is two things. One is that the academic and national lab researchers actually enjoy it very much indeed, come out of the room saying, why didn't we do this 20 years ago? And the research is accelerated considerably. Case in point, we are trying to develop new red and green emitting compounds. Used very fundamental physics, computer models in a materials genome type of campaign, came up with a dozen different compounds that could emit green light, and presented those, instead of just publishing those and then going on to work on producing all 12 and testing them, refining them, etc. We went to our industry partner, and industry partner looked at the 12 compounds and said, only 3 of those would ever be considered in our company, and they gave different reasons for rejecting the other 9. When you think that testing 12 compounds is typically a 20-year campaign, we have just saved 15 years of research.
Yeah.
So getting constant feedback from industry is enriching, enlivening, and it's inspiring to the researchers, but it's also a huge accelerator for the research itself.
Great. Thank you.
Gentlelady yields back. Ranking Member Grayson would like to ask at least one more question, so we're going to give him time to do that.
Thank you, Mr. Chairman. Dr. Jean, we have something like 300-plus light water reactors in the world. They're very expensive, something like $500 billion in replacement value for those reactors. In the United States, at least, energy production facilities are privately owned. I have to wonder, as much as I'd like to see the advancement of human knowledge in general, why is the industry not trying to add 20 years of life to a $500 billion asset? Why does this fall upon the taxpayers to do this?
So that's a very good question. So I think industry is very interested in this. I think where the value comes in with the government-sponsored research is enabling this through the tools that we've already invested in, advanced computing, the leadership class computing capability that we have, the fundamental science, speaking to Ms. Clark's question, taking some of the basic technology we have and improving that national investment into our reactor systems. So I think it adds value to things that they're already motivated doing that they wouldn't otherwise do or have access to.
Are they doing it? Are there private research facilities that actually are trying to do what you're trying to do and making any progress?
Not at the scale that we're doing it with the science that we're using.
Is the industry willing to come together and try to fund those facilities since it's for their benefit?
Well, they already are. So one thing that's important to understand about the hub is or at least our hub, is that the industry partners cost share. So they're already making investments into the hub through cost sharing and data that we couldn't otherwise have access to.
I yield back. Thank you.
Okay, I want to thank the witnesses for their valuable testimony and the members for their questions. The record will remain open for 2 weeks for additional comments and written questions from the members. This hearing is adjourned.